Causal profiling leads us to another interesting set of ideas that I would describe as simulation profiling. Right? There's something really neat there because we're doing a what-if kind of calculation that helps us to make a decision about whether we think something is worth pursuing or not. And ultimately, that idea of could we do some sort of simulation is a place where we can discover other interesting ideas. So we're going to talk about simulation profiling in just a little bit. First thing I want to talk about is called CacheGrind. And CacheGrind is another tool in the Valgrind package, and it's much more performance-oriented than the other two. Yes, memcheck and Hellgrind look for errors in your program that are likely to slowdowns caused by memory leaks or make it easier to parallelize without introducing errors. I'm presuming a little bit that you've got some familiarity with Valgrind and Hellgrind from some previous course, probably using them for a C or C++ program. If not, there's some supplementary material on this. If you take a look in the C252 notes, as I've no doubt mentioned many times, it doesn't make sense to talk about it in 459 because mostly we got like false positives out of it. Okay, but what does CacheGrind do? Right? It does a simulation of how your program interacts with cache and evaluates how you do on branch prediction. We spent lots of time talking about branch predictions much earlier on in the course, and we've also covered caching in some detail, so neither of those really needs a lot of explanation. You will recall, though, that a miss from fastest cache usually results in a small penalty that's like 10 cycles. Going to memory requires about 200, and a mispredicted branch has variable cost, but we'll say somewhere 10 to 30 cycles. So CacheGrind gives you information about the first level instruction cache, I1, L1 instruction cache, first level data cache, D1. This is the L1 data cache, and the last level cache labeled LL, which is level 3 on a CPU that has 3 levels of cache. Right? If there were more levels or fewer levels, you would get first and last, whichever those are. Sounds good. Unlike normal Valgrind operation, though, you probably want to turn optimizations on, that is compile with like the release flag, but you do want debugging symbols. But optimizations help here because they tell us something more interesting about what happens in the released version of your program. So here's a very simple sort of output from a program. If I instruct CacheGrind to run, this is an ECE 252 type example using the branch sim equals yes option. I simulate the branches prediction and misprediction because if you don't, by default, it won't show it. Okay, so great. This is going to get started. It will run, and as it executes, right, we can see that the normal program output is going to appear just as we would expect, but also we get some printout at the end that gives kind of a breakdown of what happened. So in this program, it's a simple toy example program, right? So there's actually not a lot of instructions to execute. There's 310,670 instruction references, and we missed in cache 1,700 times, and we missed in the last level of cache 1,292, right? So you can easily calculate the miss rate every time we had to go to memory to fetch an instruction. Then we have data references, and that's sort of broken down again into how many misses we had in each, and we had last level references, and finally at the end we have a bunch of information about branches and branch mispredict rates. And yeah, turns out we actually have a fairly high branch mispredict rate in this program, right? It's pretty trivial program, right? But what if I recompile this with optimizations on? It was originally a C program when I generated this data, so it's the -02 option here in GCC. And we can see if we sort of compare side by side, right, with optimizations enabled, we've dropped the number of instructions, we've dropped the number of references here, right? So we do see improvement, right? Our data and instruction miss rates went down marginally, but the branch mispredict rates went up a little bit. But there were fewer branches and thus fewer we got wrong. So the total cycles we lost in mispredicts went down, and this is in fact kind of an overall win for the code. It's just not super easy to see in this example, right? In some cases it's not as clear cut, but we could do sort of a small calculation, right? If we just look at the last level misses, there were 4,544 in the unoptimized version versus 4,487 in the first one, and we assume they take 200 cycles. And it says here the branch miss penalty is 200, but it shouldn't be 200. That should be it should be like 20, right? But we went from like 900 to 8,800 wasted cycles to 897,400, which is a decrease of about 11,400 cycles. That's not a huge amount, all considered, right? But if you repeated this for the sum of each of the measures and sum it up, it kind of makes sense. And remember also, this is a trivial program that runs in a fraction of a second. So the real benefits are observed on an actual program that runs for more time, right? CacheGrind also produces a detailed output file. It's not especially human readable, but you can ask an annotation tool to kind of break it down for you. It's the kind of thing we can do like a live demo of, because the output is pretty big for the slides. Thing about it is, like, CacheGrind is pretty verbose. It can be hard to come up with useful changes based on what you see. So what's the purpose of it, really? I mean, you can look at this and you could say, well, I don't know what to do with it. Or you can use this to identify whether a change helped or not, right? Quantifying whether a change improved on some performance critical code is good, but also giving a why is good, right? The why, as in the mechanism aspect, is very helpful in justifying to a manager or executive that the change you made actually solved the problem, and improved results are not just luck or measurement variance or something like that. You can say, yeah, we made this change and it decreased the branch mispredict rate from X to Y, and that's why this runs faster. That's a lot more convincing than, well, we made this change and it's faster and we're not sure why. Right? It's a good way to validate that your changes worked, and showing this reasoning helps a lot. We'll also talk just briefly about simulation as a form of performance debugging. So simulation allows for something else in that we can just count the number of cycles, or count the number of pipeline stalls or something. That's great. We can see how we got there. Maybe that's actionable and maybe that's not. Right, figuring out what to do out of some report that says our mispredict rate is X is not always super easy, but maybe there's some takeaway from that. But there are actually some other interesting things that we can talk about. I got looking into examples of this, and I came across some technical information for a Texas Instruments digital signal processing platform, TMS 320C55X. I've honestly never used it for anything, and I cannot say anything about it. But the interesting thing was, I was reading in the technical manual for the simulator the value of simulation for profiling. Using a simulation approach, not only can you get exact values of how often something runs or the count of how something cache misses, right? But we can also basically get like a breakpoint and halt on that event. And then we can get a lot of information that might not be available after the fact, right? We don't need as much logging or tracing or anything. Like, while we're running the code in the simulator, if we see there's a pipeline stall, let's say, right? We set the breakpoint, we stop at that point, and we can look at all the values of registers and all the values of memory and the CPU's internal state and everything. And that's really, really interesting, right? Because part of the problem that we often face is the idea of how do we reconstruct the sequence of events that led us to this problem. You've no doubt spent lots of time debugging things where, like, you can see that it's wrong afterwards, but, like, at what point did it go off the rails? Or you wish that more information had been recorded at the time that it was going to happen. I also want to talk about another thing called MIRI. So despite sharing a name with an episode of the 1960s Star Trek where the Enterprise comes across a planet that is an exact duplicate of Earth down to the continent layout, and nobody seems to think that that is an extremely big deal, MIRI is actually a profiling tool for Rust. It runs Rust code in an interpreter, which means that it's slow, but it finds bugs. So in this sense, it has a certain amount of similarity with Valgrind, which is what if we run the program slowly under observation and use that to come up with some recommendations. Okay, so MIRI, I think, based on my read of its documentation, has an intended use of detecting issues in unsafe code. Can you find array bounds violations, read uninitialized memory, memory leaks, stuff like that. It is likely that in this course you've had no occasion to use unsafe except to do launching of GPU computation. So its utility at first glance probably seems kind of limited, right? Programs that are more complex in various scenarios may require more use of it, and adding in some interop with a C library or something might be kind of interesting, right? But there might be more uses for it than we would encounter. However, we're going to consider an example because we can use Miri to generate some flame graph style results. So to run, we would need to use the Miri option, and it generates this crocs directory with some file in it, and then we process that tool, or process the file with the crocs tool to generate a JSON file that we can read in Chrome Dev Tools. Okay, so we need a bunch of things to make this work, and one of them is Chrome, so we can look at it in the Dev Tools, but that's fine. I'm sure we can find a browser that supports it. And so, yeah, to do this, right, we're going to set Miri flags on it and run the program with Miri profiling. Okay, this produces a neat little flame graph style graph that shows what calls what and what time is taken. Right, and if you prefer this, and I'm thinking about assignment 4 here, to a flame graph, that's perfectly fine. Both give you the same information in a similar way. The graphs are a little bit dense. It is somewhat challenging to sort of take a look at it. I've got some screenshots here. We could do a live demo if that makes more sense, right? But ultimately, right, like we get a nice breakdown of what called what. And so if I rect in on one thread in particular here, we're looking at the producer here, and this thread is a producer, so there's a fair amount of like setup that happens to launch a thread, right? Main is somewhat in the middle there, and then we call produce item, and we get kind of an interesting takeaway out of what we can see here right now, which is the first time this thread wants to generate a random number, because this is the producer consumer optimized version, so we're generating random numbers and putting them in the buffer. But the first time that we attempt to generate a random number, there's a huge amount of setup that happens to initialize the random number generator, right? That doesn't happen on subsequent runs, and as we can see, as the graph moves to the right, the work of generating the random number is much less. It's not nothing, but it is much less. And then we see there's little steps to sort of add what to do. Now, this is kind of cool, right? Each subsequent use of it is quick, and we learn something interesting about what's happening. Now, much like Valgrind, as I said, this makes the program run much, much slower. To make this work in a reasonable amount of time, and I admittedly am not the most patient person, I turned down the number of items per thread to 10, because otherwise I was running out of patience before it produced the results. Now, is 10 a reasonable number of items to produce? No. Am I sure that we've reached steady state in the execution of this program if we're only producing and consuming 10 items per thread? Also, no. But listen, I wanted to generate this graph. I didn't want to wait an hour for it, especially if I was going to have to do it a second time. And this is perfectly good for our purpose in terms of showing you this kind of graph. Okay. Right, so to be fair, this profiling with Miri article is referenced in the notes, got a lot of comments that said something along the lines of maybe this is helping you to optimize the debug version rather than the release one, right? You can run this and it gives you some output, but honestly you get better results by just compiling with the release flag. That is acknowledged, at least in the article, with a call out that says optimizing for Miri can actually backfire. You can end up with worse runtime performance in the release version as a result of some changes you made according to what Miri suggested. But don't treat this as Miri tells you exactly what to do, right? Miri gives you an idea of what it might make sense to change, But the intention of this, and this is true for any of the profiling tools, right, it's meant to be used in this change, run, evaluate loop. That is to say, you've got a theory about what you're going to do, and that theory may be informed by any number of different things. But at the end of the day, if you really want to know that your change worked, the only way you can actually validate that is you run it and check the results. And so, whether this is perfect or not is kind of irrelevant. You would be well advised to verify the output before you just decided, oh yeah, I'm sure that everything is fine. So that's a little bit about simulation profiling.